Yep, thanks. All right, so thanks a lot to the organizers. I'm very happy to be here. Thanks for this opportunity to talk. So this is going to be about operator entanglement, and this has not been defined yet this week, so let me go through the definition quickly. And then I'll talk about why this is interesting to some people, at least. All right, so as usual, we have a bipartition of some Hilbert space. For simplicity here, we can just take everything to be finite dimensional. And instead of looking at the state in that Hilbert space and calculate its entanglement entropy, what we want to do is take an operator that acts on this Hilbert space and ask how far this operator is from a product operator. So is it a product operator, or can we write it as a sum of two product operators, or three terms, or four terms like that, or more? So you see where this is going. So what we want to do is write something like a Schmidt decomposition for this operator. Here I'm including explicitly a normalization factor in the left-hand side, such that the sum of the squared of the Schmidt coefficients is 1. And so definition, the operator entanglement of O is the Renyi entropy of the distribution given by the Schmidt coefficients. Okay. So of course this is nothing but saying that O, which is some dA dB times dA matrix, can be viewed as a vector in a larger space of dimension dA squared times dB squared. And we are just looking at the usual entanglement entropy of that state in the larger Hilbert space. Okay, so that's the definition. Everybody okay with that definition? Okay. I must say I was the very first speaker to actually write down a Schmidt decomposition. All right, so as far as I know, this was first introduced in the early 2000s by Paolo Zanardi and collaborators. And at that time, what they were interested in was this very basic and fundamental problem. So you take some product state, psi A, psi B, and you act on it with some unitary gate. And you want to ask how much is it entangled after you've acted with U. And you want to see this as a property. Of course, the answer in general depends both on U and on the initial state, but you want to view this as a characteristic of U, of the operator itself, and not of the initial state. And so what you do is that you take some measure of entanglement, like some entropy, of the state, and then you just take the average over all initial product states for some uniform measure. And that way they define something that they call the entanglement power, which of course depends on the choice that you make for this measure of entanglement of states. And so among other things, they asked, so if the entanglement measure that you take is the Renyi entropy, is this related in any way to this operator entanglement? So the answer in general is that there is no such a direct relation. However, for the Renyi 2 entropy, so alpha equals 2, there is a relation which takes the following form. So the exponential of minus S2 of this state, averaged over all the initial product states, is some linear combination which indeed involves the operator entanglement of U. Now there are two other terms. One is the operator entanglement of U times S, and the other one is the operator entanglement of S, where S is the swap operator that exchanges A and B. That holds for if A and B have the same dimension, If the dimension is different, there's a more complicated formula. So this formula is not going to play any role in what follows. This is just to give you some flavor of what people were interested in 20 years ago when this quantity was first considered. Okay. Now, more recently, the interest in this quantity has been somewhat revived in connection with simulation of one-dimensional quantum systems or higher dimensional quantum systems, one-dimensional in particular. And there the question is, given some operator O acting on some spin chain, can you approximate it with some matrix product operator with reasonably small bond dimension? And in that context, with that question in mind, to my knowledge, this was first studied by Posen and collaborators 10 years ago. But recently, many people, so including myself, and the paper by David Lewitz and Zhu that appeared at the same time as my paper, but then also more recently other people have been interested in calculating that quantity in various one-dimensional systems. All right, and so the basic reasoning is the following. So usually, if you have a state for some spin chain, and you want to know if you can approximate it by a matrix product state, you know what you need to calculate is the entanglement entropy, in principle for any index smaller than 1. And if this is bounded as a function of system size, then you know you can approximate it. Now, if you do the same thing for an operator, you can just view the operator as a state. In tensor network notation, this means you just take so this is an operator that acts from bottom to top. You just take the bottom legs and you fold them. This gives you a state in a spin chain with twice the number of sites. And you just say, well, okay, I'm going to be able to approximate it if the operator entanglement of that thing is bounded. Now, having said that, there are two caveats. One caveat is that by doing this, by identifying operators as states in a larger Hilbert space, there is a price that we have to pay, which is that this automatically comes from a distance that we are measuring all distances with respect to the 2 norm, not the operator norm, and that might be a problem in some cases. Nevertheless, as far as I know, there's no. This is at least a quantity that you can tackle numerically, efficiently, and analytically, and I don't think there's anything equivalent for the 1 norm. So I'm just gonna ignore this. And the second thing is that, in principle, as I showed you here, the right thing to consider is the Renyi entropy with alpha smaller than 1. But in practice, we're going to use the replica trick, and so that means alpha will actually be an integer larger than 2. Now, this is what the replica trick looks like for operators. So the operator entanglement is equal to this thing here, and what's important is the numerator. The numerator looks like that in tensor network notation. So you first apply a swap operator on the part A, which permutes cyclically the replicas of part A. Then you apply your operator O. Then you swap the replicas back in part A, apply O dagger, and then you need to take the trace. So contract this bond with this bond, this bond with this bond, and so on. All right. So there is a replica trick, and that's what makes all calculations possible. All right, so that was the introduction. Now, in the rest of the talk, I want to just sketch 3 very basic results about this quantity that you can get very easily with some basic exercises in 2D CFT. And then, but I believe these are already interesting in terms of what they mean for matrix product operators and approximability of operators in terms of MPOs. And second, I will turn to the operator entanglement of Heisenberg picture operators, which I think is an interesting problem, and that is not solved yet. So I won't enter the CFT calculations in any details, at least not for that part. Okay, the only thing I'm going to say is that you just have to adapt the standard trick. So you map the replica trick to a calculation of correlators of twist fields. We've already had some talks about that. So this is, of course, what the technology was that was developed by Pasquale, John Cardy, and many other people, including Olaja, Benjamin, that has been used by many people, Hubert, Jean-Marie, myself, others. So the first very basic result I want to present is just that if you take an infinite line and you are interested in the operator entanglement of the evolution operator, this blows up linearly in time. So this is very simple, very basic. And so this comes out of the CFT calculation, but in fact, similarly to the case of the linear growth of entanglement after a global quench that was first pointed out by Pasquale and John Cardy, which turned out to be much more general and be a conclusion that was valid much beyond CFT. This generic linear growth seems also to be true in many other systems, so not just CFT, and this was also observed by other people, especially in this paper by Adam Nahum and collaborators. They developed a coarse-grained scenario for chaotic spin chains, where this linear growth also comes out naturally. And what this means in terms of approximability by a matrix product operator is that if you take the evolution operator, which you may represent as a circuit like this, with some, which is a Trotter decomposition, so you do a bunch of Trotter steps. So the circuit you get looks like this, and the question you ask is, can you reduce this to so can you compress this? Can you reduce the bond dimension here efficiently? Can you write that as an MPO? And the answer is no, because the operator entanglement between A and B blows up linearly, so that you expect the bond dimension here to go exponentially with time. Okay, now another very basic result is for the thermal state. So the Gibbs state, so again you take an infinite line. This time instead of looking at the evolution operator, we look at the thermal density matrix. Calculate the operator entanglement, and this time we see that this goes as a constant, as a function of system size. So it doesn't depend on system size. Which means that we have some sort of an area. Well, we have an area law for this operator entanglement, and so what this means in terms of approximability is just that if you take a Gibbs state, then you can write it as the same circuit as earlier, but this time there's no I in the exponential. So that's the only difference. And this time compression is going to be possible, so it's going to work because this operator entanglement is small. And okay, so this is what this thing suggests. But of course, this is very well known. It has been known forever in matrix product states, and in the tensor network community. It has been exploited a lot numerically by everybody. And it's even been proved mathematically rigorously by these people. So nothing new here. It's just that it's a very simple result that is fully compatible with what's known. And the third basic result I want to tell you about is for a quench. So you take an initial state that is short-range correlated, so that is short-range correlations only. So you think of a product state, and you apply the evolution operator on it. And the question you ask is, you take the reduced density matrix of some finite interval, and the question is it possible to approximate this the reduced density matrix of this finite interval by a matrix product operator? And yeah, so you expect this to be feasible somehow, at least at very short times, because at very short times this can be approximated by an MPS, and so the projector on this state is an MPO naturally. And so at very short times this should work. At very long times it should also work, because this is supposed to go to a Gibbs state or some generalization of a Gibbs state, which is also approximable by an MPO. That's what we just saw, because the Gibbs state has an area law. So it looks like this is a good idea at short times and at large times, but the question is, does anything happen in between? And to answer that, what we need to calculate in principle is the operator entanglement between A1 and A2, where we take some bipartition of this interval like this. And this is going to give us some idea of how the bond dimension at this position here is going to grow with time. And the answer is that it actually blows up at intermediate time. So these pictures are very similar to the ones that Vincenzo was showing yesterday. So what happens is that initially it goes linearly. This is the CFT calculation, the dashed line here. So initially it grows linearly, and then it decreases also linearly, and then it just stays to some finite value. Yeah, so if you actually do the calculation in some real spin chain, here I did it for some free Fermi system for large system size, you see that indeed this is what happens. It initially blows up and then it decays. So the decay is not really captured by CFT, so there are other effects, and that's why it decays slowly, more slowly than the CFT calculation. But what matters really is that it blows up at intermediate times. And okay, very, very similar results had been obtained earlier by Pasquale and Eric and Koser. Actually, the calculation for this for the operator entanglement just follows from adapting their calculation. All right, so these were the three basic results I wanted to tell you about, and now I'm going to turn to a question I'm more excited about at the moment, which is the operator entanglement of operators in Heisenberg picture. So there, the motivation is the following. So 10 years ago, these people here proposed to look at DMRG or DBD in Heisenberg picture. And what that means is that, well, usually when you do time evolution in a spin chain, where you're typically interested in calculating the expectation value of some observable at time t, starting from some initial state psi naught here. And when you do standard TEBD, what you do is that you evolve the state and approximate the state at each time step by some matrix product operator. But you could do something else. You could try to approximate the operator phi of t by a matrix product operator. And if you could do that efficiently, then you would be able to calculate that expectation value. So the problem with approximating the state by an MPS is that the entanglement entropy blows up linearly. Maybe if the operator entanglement if the operator entanglement of this thing increases less than linearly, then at some time, at least, it's going to be more efficient. So that was the idea, but somehow it didn't it didn't take off. So there must be a reason why this in fact doesn't work. But anyway, so so what you would do on a computer would be that you would start from a local operator here acting on some site. Everywhere else it's just the identity, and then you do again a trotter decomposition. You evolve the top row forward in time, the bottom row backwards in time. You do this several times, so you grow your circuit like that. Notice that because this is just the identity and this is a unitary operator and this is its adjoint, it actually simplifies. So the circuit you need to consider looks more like this. So you naturally have some sort of light cone effect that is automatically built in. And what we want to calculate is the operator entanglement of this operator at time t at position x, where x is the distance between the original site, at site 0 is a position 0 here, and the position of the cut between A and B. All right? So we have a quantity that depends on x and t. That is defined by this. So this is the problem. Now I have one technical slide that is aimed at CFT experts, and then I'll come back to just the results. So it turns out if you want to calculate this in CFT, it maps to an out of time ordered correlator, because you need to calculate some trace of twist fields inserted at time 0, and your operator phi replicated at time t. And to make sense of this in a CFT calculation, you need to regularize things. And one natural way to regularize would be to smear the operators, which means that it's like doing the calculation at a very large but finite temperature. And if you do that trick, then by applying some technology that was already used by other people some time ago, you can just show that at large time and at position 0 here, I'm just writing the position at 0 for simplicity. So at large time, this goes either to a constant, if this constant is non-zero. This constant turns out to be some coefficient of the F matrix. So either it goes to a constant when it's not 0, or if this constant is 0, then it goes to some then it goes exponentially, it decays exponentially with time. And since the operator entanglement is essentially the log of this thing, you see that the operator entanglement either goes to a constant or just blow up linearly with time. So if you include also the x dependence, then the result looks like this. So either things just remain bounded at any time, like that. You still have some light cone effect because automatically at 0 for x larger than t, velocity is 1 here, and non-zero in some for x smaller than t, but the point here is that it remains bounded at any time, or it blows up linearly with time at here, and the shape looks like a pyramid like that. Okay, and these are the only things. These are the only two cases that you can have, at least with that kind of regularization. Now, if you look at what happens in a real system, in a spin chain, so in the case of a chaotic spin chain, which was studied by these people here, then indeed, what you see is that the operator entanglement takes the form of a pyramid, like this. It's a function of x, and it's a pyramid that grows roughly linearly in time. So that corresponds precisely to that case here. However, it's not supposed to apply. I mean, there's no CFT here. It's not. It's just some. This is just. They did the simulation in a quantum chaotic Ising chain. It's not supposed to be. It's not supposed to be directly related to a CFT. But still, qualitatively, it looks like it's the same behavior. And if you actually do the calculation in a free fermion chain, then it's completely different. It doesn't look like a pyramid at all. So the operator entanglement takes the form of these curves here. And what's really important here is that although the front here still moves ballistically, the top, the maximum of the curve, doesn't blow up linearly in time, but it blows up only logarithmically. So the operator entanglement is grows at most logarithmically in time for free fermions. That was an observation that was already made by Posen and Pijorn 10 years ago. But what I'm going to explain is where these curves actually come from. So it's a bit, you see, the situation is a bit strange because I didn't assume anything about the CFT, so I could be applying this to the Ising CFT. And this would give me some result for the Ising CFT, but this clearly doesn't fit. And this is supposed to be described by the Ising CFT. So there's something that doesn't work. And more generally in the integrable system, in integrable spin chains, what seems to happen is that it's sort of an intermediate case. So it's again, it doesn't give a pyramid. It gives some sort of rounded curve like that. And again, the front moves ballistically, but the maximum of the curve grows up neither. It seems to grow neither linearly nor well, somewhere in between linear and logarithmic. So it's faster than logarithmic, but slower than linear. And this is not understood yet, but we think that we can adapt some of the technology that Vincenzo was explaining yesterday to tackle this case. Any questions? Yeah. Spins. Well, this is TBD, so it's you can take as. I think this picture was done by Vincenzo. I think it's 40 spins. Vincenzo, question for you. How many spins? Okay. Yeah, exactly. It's the system size is not a limitation. What's a limitation here is time, right? It's TBD, so you can do very, very big systems. The problem is to go at large times to see what's happening here. So okay, so you know this kind of nice CFT calculation actually doesn't give. It doesn't seem to give to tell us anything about the real behavior of this spin change. And the problem it can be just tracked back to this smearing, which just happens not to be. It's a specific regularization scheme. It just turns out to have nothing to do with what's actually happening in a spin chain. So essentially, you can just forget about this calculation, unless you're interested in the chaotic case, and seems to say something about the chaotic case, although I'm not even sure it's supposed to apply in that case. But anyway, so it's kind of strange. And now let me explain what we have to do instead to get at least the result for the free fermion case. So now in the last few minutes, I'm just going to focus on the free fermion case. So, okay, so for concreteness, I take the XX chain, and I'm going to focus on the operator sigma x at position 0 at time 0, and that I evolve in time, right? And Now, the key point to understand what's going on is that sigma x is the endpoint of a Jordan-Wigner string in fermion representation. And so the problem boils down to understanding the operator entanglement, the growth of the operator entanglement of a Jordan-Wigner string. So that's what I'm really going to study. So not directly the operator sigma x, but more the Jordan-Wigner string, really. So the Jordan-Wigner string is just like that. So it's a product of -1 signs, depending on the occupation number of each site, and I'm taking the product over all spins on the left side of the system, left side of the cut, right? Yes, and then I evolve this with time, and I want to calculate the operator entanglement of that operator. So this can be done as follows. So again, one convenient way to think of this is to view the operator as a state in a larger space. For free fermions, this just means that we are going to replace the operators that annihilate a particle by an operator that creates a sort of an auxiliary particle. This is just a way of rewriting things, and now we see this as a state in this n-large Hilbert space. We do some Bogoliubov transformation, and we arrive at the following system. So this Jordan-Wigner string turns out to be exactly a product of two completely independent states, which look like that. So it's now a lattice system that is completely filled by particles on the left and completely empty on the right, and we get two copies of that. One for these Bogoliubov particles. Yeah, sure. Yeah, sorry. This is a typo. It should be D. Yeah, thanks. And I didn't write the Hamiltonian, but the Hamiltonian also sort of factorizes under this operation. And so then what we end up with is two independent copies of the following problem. So we have a chain that is initially filled by particles on the left that are hopping from left to time, from left to right at times larger than 0. And at large times, what happens is that there's some profile that develops that looks like this, that in the free case at least has been known for a long time. And the question that we need to answer in order to calculate the operator entanglement is how are we going to describe the fluctuations in that part here from CFT, and then if we can do that, then we just again apply the twist field trick, and that's going to give us the result. So we go to imaginary time because it's convenient to think in imaginary time. And in imaginary time, what we have is this kind of problem. So we have our initial state, which is now completely filled with particles on the left, completely empty on the right. We evolve in imaginary time, and we project back to the initial state. Now, okay, so if you are familiar with some of the usual CFT papers on entanglement entropy, this is very standard. What is highly non-standard, however, is that this initial state, this corresponds to some CFT living on a strip with some boundary condition, but this boundary condition is not a conformal boundary condition. That's the big difference with the usual case, and that's just because this is here you have some finite density, and so you can't just rescale things because. And so it's convenient to think about this to make the connection with some other types of problems. So here what I'm representing is a particle that starts from here this green line is a trajectory of a particle that starts from here and arrives here. Okay, and it does discrete. There's a discrete time evolution, and they can hop to the right or hop to the left. And you see that these trajectories of particles, they map to some sort of domino. Losange tiling problem. Okay. Like that. Sorry? Okay, so you imagine that you have all these sides on this side are filled with particles, and so you have these trajectories, and each configuration of particles on the left that are hopping from bottom to top maps to some configuration of losanges like that. Okay. Now, when the systems becomes bigger, when the system okay, so now we just erase the trajectories, and when the system becomes bigger, you see that this kind of phenomenon occurs. So what you're supposed to see here is that there's a sort of a limit shape, and there's a limit shape that emerges. So the degrees of freedom are completely frozen on the right, completely frozen on the left, but then there's a region in the middle that emerges that looks like an ellipse here, where the degrees of freedom are actually fluctuating. And so this kind of problems has a long history, both in physics and math, and also in computer science, and it's been dubbed Arctic Circle problem by these people. Shor is Peter Shor from the one you know from the Shor algorithm. Sorry. So Filippo Colomo is I guess in the audience somewhere. So he's one of the big experts of this type of problems. He's from here, from Florence. So the problem maps to some kind of problem like this. Yeah. Okay. Thanks. And sorry. So what we get is an Arctic Circle problem of this type. So the operator entanglement is actually related to a problem of this type. And so what we need to figure out is what is the field theory that is describing the fluctuations inside this shape. And for the domain rule quench in the XX chain, we had done that, and it turns out it's just a CFT you would expect, but in a metric that is not the standard Euclidean metric. But if you know that, then you can do the calculation. So you calculate the entanglement entropy by inserting one twist field. You calculate the correlation function, do the Wick rotation, and that's it. You get this result, and indeed you get the log that is observed in the numerics. So it's a completely different kind of regularization. It's not the smearing. The smearing doesn't help here. You really need to go back to the lattice and see the full physics, and not just the CFT limit. And if you do that properly, then you can get this operator entanglement. So that's it. As I tried just to highlight this quantity, I think it's interesting because it's a quantity you can calculate. And the problem of operator entanglement of Heisenberg picture operators is still open, at least in the integrable case. And I think it's interesting, and we're trying to do something with Vincenzo on that. Thanks.
It is on. So how important was it for this calculation that you were looking at the Jordan-Wigner string and not at the local operator of the fermions? Like if you decided to look at something that was sigma z as opposed to sigma x, you would you have gotten something that agrees with the CFT calculation?
Yes. Okay. Thanks for this. So I skipped that just to make things simpler, but yeah. So you're absolutely right. So if you take sigma z instead of sigma x, then there is no Jordan-Wigner string, and then the answer is just that it's just. In fact, you can easily see that it's an exact MPO. So sigma z of t in a free fermion system is just an exact MPO with bond dimension 4. You can just write it down. So the operator entanglement is bounded. That was known to Posen, and that was actually known to these people who came up with this idea of DMRG in Heisenberg picture. That was the basic observation that actually motivated this idea. That for free fermions, indeed, there are some operators that are just exact MPOs with very small bond dimension.
Other questions?
So what is wrong with smearing in the CFT? Any intuitive idea?
Well, it's just that you know, some problems are just not CFT, right?
So do you mean it's not in the CFT, or it's just that you should smear it differently?
No, so it's really that the real problem is the spin chain. The real problem is in the spin chain, and you're really asking a question about the spin chain. And if you start by saying, well, let's look at very small small excitations around some energy that you've chosen arbitrarily, well, okay, you can do a calculation. But if the effect you're looking for is just a totally different energy, then this doesn't work, right? And this is what's happening here. So because the problem becomes very inhomogeneous, you see, so the density is strongly varying from left to right, and so if you're just trying to look at this as a CFT that would capture the physics of say to close a half filling, so low energy excitations around the Fermi surface, the half filling, then this is going to be a good description, maybe in the middle, but of course far away it's just completely wrong.
Other questions? Okay, then let's thank the speaker again.